It's Paul, now ready to tell you the modern way of finding eigenvectors and eigenvalues. You really ought to look through sections 1 through 3, 1.4 and 1.5 of the executive summary before starting out on this. This approach was introduced in 1995 in the famous article Down with Determinants by Sheldon Axler. It's used in John and Barbara Hubbard's textbook. It is still not used in all linear algebra texts, many of which were written before 1995, but it is the accepted way of finding eigenvectors and eigenvalues these days. Let's start with the same matrix we used last time. This is the now familiar matrix A, but the technique is quite different. I pick a vector W. The first standard basis vector is as good a choice as any. Apply A to it, getting the first column of the matrix A. I now have two linearly independent vectors, and when I calculate A squared W, I now have three vectors in R2. They have to be linearly dependent. I can confirm that by making them into the columns of a matrix, which I'll call T, and if I row reduce T, I can figure out the exact nature of the dependence. The third column, remember, comes from A squared W, and what the row reduced matrix says from the first row is that that's equal to minus 3 times W, or minus 3 times the identity matrix times W, and the second row says we have to add on 4 times A times W. If I write that equation with everything on the left, I get A squared minus 4A plus 3I acting on W equals 0. And if I write this quadratic as a function of T instead of a function of A, it's T squared minus 4T plus 3. You may in fact remember the characteristic polynomial from the earlier script. We found the same polynomial again, but as you will learn, that doesn't always happen. I can factor P into two linear factors, and when I do that using A as the variable, I say P acting on the matrix A is A minus AI times A minus 3I, and now I have a wonderful way of finding eigenvectors. I argue that if I start with the vector W, hit it first with A minus 3I, and then hit it with A minus I, I'm going to get 0. If I hit it only with A minus 3I, I construct a vector V1, which gives 0 when I hit it with A minus I. In other words, it's an eigenvector with eigenvalue 1. The two factors commute with one another. All polynomials in a given matrix commute with one another, and therefore I can reverse the order of the factors, and now I argue if I hit W with A minus I get a vector V2, which has to be an eigenvector with eigenvalue 3, because when I hit it with A minus 3 times I get 0. Well, we found two eigenvalues, two eigenvectors, not much more to learn. We can try using a different W, like the second standard basis vector. The process goes through exactly the same way. We get exactly the same polynomial. We construct a pair of eigenvectors by exactly the same technique and confirm that they are indeed eigenvectors. We didn't find exactly the same eigenvectors, but we found ones that were proportional to the ones we already knew about. For example, when I compare V1 and V1x, I discover they differ by an overall sign. And when I compare V2 and V2x, I discover that I get one from the other by multiplying by negative 2. Now let's think about how this process could fail to find all the eigenvectors in one fell swoop. Suppose I start with the vector 1, 1. You may already have noticed that that is one of the eigenvectors, and you say, what a clever choice. You're going to find an eigenvector right off the bat, Paul. Indeed, when I calculate A times W, I discover I already have two linearly independent vectors. I bind them together into a matrix. Now there's a matrix that is really easy to row reduce. Subtract the first row from the second row, get a row of zeros on the bottom, and the top row tells me that A times W equals 3 times W. So my polynomial in this case, as a polynomial in A, is A minus 3i, and I see that W is an eigenvector with eigenvalue 3. Now, if I want a second independent eigenvector, I have to start over again with a different value of W, and that will reveal the eigenvector with eigenvalue 1. I will be showing you so many examples of this process that I won't bother doing the details of that. Let's instead worry about what might happen if there are fewer than two distinct eigenvalues. Let me start by cooking up a 2 by 2 matrix that clearly has only one eigenvalue. This matrix A is 4 times the identity matrix. It multiplies any vector by 4. So the first standard basis vector is an eigenvector. It gets multiplied by 4. I could construct the matrix T and learn the same thing, but there's no big surprises here. The surprise comes when I look for a second eigenvector. As W2, I will use my second standard basis vector. Yep, that's an eigenvector 2 with eigenvalue 4. I can determine that by row reducing T and getting the polynomial A minus 4i for a second time. I found another eigenvector for eigenvalue 4, but this is a different one, or more precisely, it's an independent one. We found the two standard basis vectors are eigenvectors. To summarize what happened here, for either choice of W, the polynomial P of T was simple. It had no repeated factors, and we found a basis of eigenvectors. And notice in this case, the characteristic polynomial is equal to A minus 4i squared, or as a function of t, t minus 4 squared. So in this case, in neither case was P of t the same as the characteristic polynomial. Now I've cooked up another 2 by 2 matrix that has only one eigenvalue. Here's my matrix A. I choose my first standard basis vector as W, hit it with A and A squared, make a matrix, row reduce it, and interpret the result. This says the third column, A squared W, is from the first row, minus 16iw, plus from the second row, 8aw, and my polynomial therefore turns out to be t minus 4 squared. That means if I hit W twice with A minus 4i, I will get 0, or equivalently, if I hit it once to get a vector v, then hitting it a second time with A minus 4i will give 0. In other words, v is an eigenvector with eigenvalue 4, as I can easily check. I can try different values of W all day. Here I'm trying with the second standard basis vector. But all I get is this same old polynomial, t minus 4 squared, and the same old eigenvector with eigenvalue 4, because there is no second eigenvector. To summarize what happened in this case, the polynomial P of t was not simple. It had a repeated factor, and we could not find a basis of eigenvectors. And this is going to turn out to be the general rule, which will be one of your proofs. We can find a basis of eigenvectors if and only if, when we use this process for each of the standard basis vectors in turn, we always get a simple polynomial P of t. Now let's look at the case of a 3 by 3 matrix. I'll use the one from the textbook. And why not use the first standard basis vector as W? Since I have 3 component vectors, I will compute 4 columns for my matrix, guaranteed to give me linear dependence. I row reduce the matrix T, and from that matrix I can read off the equation a cubed minus 4a squared plus 3a equals 0. This was chosen for the textbook, I'm sure, because having a as a factor, although it's cubic, it's easy to factor completely. Here's my polynomial as a function of t, and if I plot it, R shows me that the graph of P intersects the line at 0 3 times, and the 3 roots of this polynomial are 0, 1, and 3. Now let me show you how to get 3 eigenvectors. I picked 2 of the 3 factors, say the ones corresponding to 3 and 1. Hit W with a minus 3i, and then hit it with a minus I. If I were to follow that by hitting it with a, I would get 0. It follows that I have constructed an eigenvector for eigenvalue 0. If I apply to W a minus 3i followed by a, but don't use a minus I construct a vector v1 on which a minus I gives 0, in other words, an eigenvector with eigenvalue 1, and using the third pair, a minus I and a, gives me the eigenvector for eigenvalue 3. But there are choices of W for which I don't get all 3 eigenvectors. If, for example, I chose W equal to V3, I would immediately find that A times W was a multiple of W, and I would find 1 eigenvector, 1 eigenvalue, no more. Here's a more interesting variant of that. I will choose W to be the sum of V1 and V3. Knowing what's going to happen, I apply A only twice. I get a matrix T. I row reduce it. I look at it and say, haha, the polynomial in A is a squared minus 4a plus 3i equals 0. P as a function of t is just quadratic, and when I plot it, I find not 3 roots. A quadratic cannot have 3 roots. I find only 2 roots, 1 and 3. I can get 2 eigenvectors all right. I apply a minus 3i to W. I construct a v1 on which a minus I will give 0. That's my eigenvector for eigenvalue 1. If I apply a minus 1 times I to W, similarly, I get the eigenvector for eigenvalue 3. But I don't find the eigenvector corresponding to eigenvalue 0. In order to find that, what I'd have to do is choose a W that is not in the subspace spanned by V1 and V3. Now here's a really interesting example. Another 3 by 3 matrix A. As my first choice for W, I will use the first standard basis vector. You say, that's a silly choice. That's already an eigenvector. Well, you're absolutely right. I only need to multiply W1 by A to get linear dependence. I will row reduce to be systematic about this and find that a minus 2i equals 0. So W1 is indeed an eigenvector with eigenvalue 2. I'd like to find more eigenvalues, more eigenvectors, so I choose a different W, this time the second standard basis vector. In this case, I have to use AW and a squared W before I get linear dependence, but now row reduction reveals that. I find that a minus I times a minus 2i acting on W2 gives 0, and therefore when I hit W2 with just a minus 2i, I find an eigenvector for eigenvalue 1. When I hit W2 with just a minus I find an eigenvector with eigenvalue 2, but it's not the same eigenvector with eigenvalue 2 that I found earlier. That was the first standard basis vector. This v2 is not. So we found a basis of eigenvectors. One of them has eigenvalue 1. The other two have eigenvalue 2. In this case, because there are only two distinct eigenvalues, there's no clever choice of W that I can make that will give me the entire basis of 3 eigenvectors. P of t is guaranteed to be simple in each case, and therefore, since there are only 2 possible roots, it can be at most quadratic. It can't be cubic. Finally, let's look at an example where there is no basis of eigenvectors. I'm not going to read these next 4 lines, but this is how I cooked up the matrix A, and now I'm going to multiply it by 2 to make it have integer entries and start out with that. Start with the first standard basis vector. Yet again, apply various powers of A, make a nice matrix. I'm certainly glad we have rough at our command. When I row reduce that, I can read off the polynomial t by just using the coefficients in the last column. T cubed minus 12t squared plus 48t minus 64 equals 0. And when I plot that, I quickly discover that the only root of this cubic polynomial is 4. Indeed, this cubic polynomial is t minus 4 cubed. That's not simple because it has a repeated factor. If I compute a minus 4 times I cubed, I get the 0 matrix. So I can find an eigenvector all right. I start with W. I hit it with 2 factors of a minus 4i. Now I've constructed a vector v, which will give 0 when hit by the 3rd factor. It's an eigenvector with eigenvalue 4. But that's the only eigenvector. So here's what's emerging and what we need to prove. First, eigenvectors that correspond to distinct eigenvalues are always turning out to be linearly independent. And that's going to turn out to be very easy to prove. Second, a basis of eigenvectors will exist if and only if, when I use each standard basis vector in turn as W, in each case the resulting polynomial P of t has simple roots. In other words, the existence of a polynomial P of t that has a repeated factor tells me that I am never going to be able to find a basis of eigenvectors. Now you've got the technique, and in the next script we can do some examples using eigenvectors and eigenvalues.